Hello and welcome to this video in which I will show you how to specify an autoregressive cross-legged model for longitudinal data in Mplus. My name is Geiser. I'm an instructor and statistical consultant with QuantFish, and on this channel I present weekly statistics tutorials. On Tuesdays I usually show an analysis in the Mplus software, and on Thursdays I talk about more general issues in multivariate statistical analysis, including structural equation modeling, factor analysis, multi-level analysis, and latent class modeling. If this is something that interests you, then please subscribe to this channel. Also, don't forget to hit the like button and to check out the description for additional free resources, including a link to my weekly statistics newsletter, as well as courses that I teach for QuantFish. In this video, I'm going to show you how you can specify an autoregressive cross-legged model for longitudinal data in the Mplus software. What is an autoregressive cross-legged model? It's a special type of path analytic model that we can use to look at the relationships of repeatedly measured variables over time. So looking at how a variable at time 1 influences itself over time in a so-called autoregression, as well as the impact that it might have longitudinally on other variables while controlling for their autoregression as well. So it's intuitively one of the natural models that we use when we look at causal effects over time, when we're interested in looking at whether A causes B or B causes A longitudinally. It allows us to find out, is it more likely that one variable is the cause of another, or is it the other way around? Now, that being said, so say an autoregressive cross-legged model cannot prove causation unless you have a very strong experimental design with an experimental manipulation, but at least it is better than a pure cross-sectional regression model where you look at the relationships of variables at the same time, and an autoregressive model at least allows you to rule out certain relationships. If you find that they are not present, then at least you know, so say that there's not an effect. So let's dive into it and let's take a look at the Mplus syntax first for specifying an autoregressive cross-legged model. You can see here in my data file I have 4 variables. I have the memory scores of individuals measured at time 1, and then I have a subjective well-being score at time 1 where individuals rated their mood states, and then also I have the same variables at time 2 again. And so now I can look at the longitudinal relationships of those variables using an autoregressive cross-legged model. Notice also that there are missing values in the data set, and the missing scores are coded as 999 for all 4 variables, and I'm telling Mplus this here so that it will take missing scores into account, which, as we will see in Mplus, is really straightforward using full information maximum likelihood estimation. In the model statement, I specified the autoregressive cross-legged model, and so you can see that it's a special type of path analysis where we have multiple regression equations estimated simultaneously in this multivariate model. And so the first regression equation here is for memory 2. Memory 2 is regressed on memory 1, so that would be the autoregressive effect or autoregressive slope coefficient for memory regressed on itself across time. And in that same regression we also estimate the cross-legged path, so from subjective well-being 1 onto memory 2, and so this allows us to study the longitudinal relationship between subjective well-being and memory performance. So is it the case that memory performance longitudinally depends on subjective well-being at time 1 when we also control for the previous memory score, memory 1? So the whole idea, or one idea, of the autoregressive cross-legged model is to look at effects of other variables above and beyond the autoregression. So while controlling for the autoregressive stability, is there an effect of another variable over time? We do the same thing also for subjective well-being. We predict the subjective well-being scores at time 2 from the subjective well-being scores at time 1. So that's again the autoregressive effect, this time for subjective well-being. And then in addition, we're looking at whether memory performance at time 1 has an impact on subjective well-being at time 2. So that would be the cross-legged effect from memory onto subjective well-being. Assuming that these are continuous variables, which is the default setting in Mplus when you don't define variables as categorical in the variable statement, what will happen is then that a linear regression will be estimated for those regression equations, because these variables are not defined in any specific way as categorical, and so Mplus will assume that they are continuous variables and therefore will use linear regression coefficients in this path analytic model. So that's to say all we need to specify for the autoregressive cross-legged model. Mplus by default will estimate the covariance between the exogenous variables, subjective well-being 1 and memory 1. Those are the variables that are not influenced by other variables in this regression model. They are purely exogenous, and they can be correlated, and their correlation will be taken into account like in multiple regression analysis when estimating the path coefficients or autoregressive cross-legged effects. What Mplus will also include by default is the residual correlation between the residuals or error terms for the endogenous variables memory 2 and subjective well-being 2. Remember, those are the dependent variables. They appear on the left-hand side of the on statement, and so they have error terms associated with them automatically, because we're assuming that they cannot be perfectly predicted in the regressions, and so those error terms then also are allowed to correlate in case there are time-specific influences at time 2 that they share, and so this covariance or correlation will be estimated automatically by Mplus. Another thing that is worth mentioning is that I listed the variance parameters for the exogenous time 1 variables here explicitly, and the reason why I did that was to more explicitly bring those variables into our missing data model for these analyses. Mplus uses full information maximum likelihood estimation with missing data by default, and so automatically missing scores are included if there are any, however only for the endogenous variables. So the exogenous variables will not automatically be part of that full information maximum likelihood estimation, or more precisely the missing scores. If there are any missing scores on exogenous variables, then Mplus will not include them unless you explicitly mention parameters for those exogenous variables. And so that can be done by just simply mentioning their variances in the model statement, and then Mplus will include missing scores also on the exogenous variables, which is what you would typically want, and you wouldn't want to throw those data away. I then requested also the standardized solution STDYX, so that we can take a look at standardized path coefficients as well as also R² for the endogenous variables. Let's take a look at the output file. You can see that there were 272 observations here in the sample. We can see that memory 2 and subjective well-being 2 were listed as continuous observed dependent variables, and then observed independent variables were memory 1 and subjective well-being 1, as it should be. Mplus by default for continuous outcomes uses maximum likelihood estimation, and here with missing data, as we will see shortly when we take a look at the missing data information. Under summary of data, you can see there were 3 missing data patterns. Those aren't listed by default. If you wanted to take a look at the missing data patterns, then you would have to include the pattern subcommand in the output command. So if you included a keyword pattern here, then Mplus would also give you the missing data patterns. But what Mplus does give you is the covariance coverage information, which shows you how much data was actually available to estimate each variance and covariance. You can see, for example, from the covariance coverage matrix that 79% of cases contributed information for estimating the memory 2 variance, and 68% were included for estimating or provided information to estimate the covariance between memory 2 and memory 1. So overall covariance coverage was decent. The lowest one was 68% for these across time covariances. There was the most missing data was, to say, for the across time covariances, because some individuals provided only data on either time 1 or time 2, and so then they didn't provide any information to estimate those across time covariances. But overall, this was still decent covariance coverage. When we look at the model fit information section, we first of all can see that the model estimation terminated normally, which is a good sign. So there were no estimation problems here, no improper solutions. And then when we look at the fit statistics, we find that this model is saturated. You can see that from the chi-square test of model fit, which yields a value of the test statistic of 0 and has 0 degrees of freedom. And so that shows you that this model was just identified or saturated. And the reason for that is that all possible relationships between variables were estimated. The 2 autoregressive paths were estimated. The 2 cross-legged paths were estimated. The exogenous variable covariance was estimated, as well as the residual covariance. And so there was nothing left over in terms of the covariances, and also the variances and means were all used to estimate parameters. Now, this would be different if we hadn't estimated, for example, the time 2 residual covariance, or if one of the direct paths, one of the cross-legged paths was explicitly or implicitly set to 0, then there would be degrees of freedom in this model. But as is, it's saturated, given that all possible paths here were included, as we will see from the model results section. Therefore, the fit statistics here are not interesting. Perhaps what is interesting is the chi-square test of model fit for the baseline model. The baseline model in Mplus is the independence model, which assumes that all covariances between variables are 0 and that the variables can only have means and variances, so that it's a null model, a null relationship model that assumes that all those 6 covariances here would be 0 and in the data, so all the off-diagonal elements would be 0, and so that here is not the case. There are relationships that are quite strong between some of the variables, and therefore the baseline model chi-square test rejects the baseline model. So this is a significant chi-square, highly significant, indicating that there are substantial relationships between at least some of the variables, and therefore it does make sense to estimate a model, for example, an autoregressive cross-legged model that models the relationships between those variables. The model results section then gives us, first of all, the path coefficients, and so here you can see that first we get the autoregressive effect from memory 1 onto memory 2 with an unstandardized coefficient estimate of 0.753. This coefficient is statistically significant, as you can see here from the small standard error relative to the point estimate. The Z statistic is large and highly significant, indicating that there is significant stability in inter-individual differences with regard to memory performance, which makes sense. So memory scores over time are pretty strongly correlated. And also you can see that there's no cross-lagged effect from subjective well-being at time 1 on memory performance time 2. This coefficient is close to 0. It is smaller than its standard error and yields therefore a test statistic that is also really small, as well as a p-value that is large and not statistically significant. So there would be no cross-lagged path here, no significant cross-lagged path from subjective well-being onto memory performance longitudinally. For subjective well-being, we find that there's also a significant autoregressive path here. 0.457 is statistically significant. So there's also significant stability in subjective well-being scores over time, as we would expect. And in addition, there's also a significant cross-lagged path. So memory performance at time 1 influences subjective well-being at time 2 above and beyond the autoregression. So this path here is also statistically significant. So there is, in this case, a significant cross-lagged effect from memory performance onto subjective well-being at time 2. And so that would be the effect that we would be particularly interested in. Is there a cross-lagged effect that is significant? You can furthermore see that the residual association between the subjective well-being scores, or the residuals for the subjective well-being scores at time 2 and the residual scores for the memory performance at time 2, is close to 0. This is a covariance because this is the unstandardized solution. So this covariance here is very close to 0 and not statistically significant. You can see the p-value is 0.812. So there is no significant or substantial residual association at time 2. So that parameter could be dropped from the model without a loss of fit. And then you would have actually a chi-square test with 1 degree of freedom if this residual association had been dropped or had not been estimated, and the model probably would still fit, given that this parameter is not important, not substantial. In contrast, the correlation between the exogenous variables at time 1 is larger and is also statistically significant. So there is a moderate sized and statistically significant positive correlation between the subjective well-being scores at time 1 and memory performance at time 1. Now here from this coefficient you can't really see that it's a moderate size association because this is a covariance, but later on when we look at the correlation we will see that. So when we look at the standardized solution we'll see that this corresponds to a moderate size correlation in this case here. Notice this is the covariance at time 1, and here we can also only see it's positive and it's statistically significant. We can't really judge the magnitude from this coefficient because it's not standardized. It's a covariance, not a correlation. We get the means of the time 1 variables here, as well as the intercepts for the endogenous variables. Also we get the variances estimated for the exogenous variables and residual variance estimates for the dependent variables at time 2. Below that is the standardized solution, where we find standardized path coefficients. You can see here again that there is an autoregressive effect for memory performance. The standardized coefficient is quite strong, almost 0.8. For subjective well-being, the autoregressive coefficient is not quite as strong, about 0.44. The memory performance cross-legged effect is also relatively substantial, 0.35. And here you can now see the correlations, because this is the standardized solution where we find the residual correlation is negative 0.017, which is close to 0, and again it's not statistically significant, so that residual association at time 2 could be dropped from the model. The correlations between the exogenous variables is 0.352, and that's a moderate size association at time 1, and it's statistically significant, as we can see here from the small p-value. And then lastly, at the bottom, we get R-squared estimates for the endogenous variables at time 2. In this model, about 64.7% of the variance in memory performance at time 2 can be explained by both the autoregression and the cross-legged effect, where here the cross-legged effect is not significant, so there's not much coming from there. For subjective well-being, a total of 42.3% of the variance at time 2 can be explained by the autoregression and the cross-legged effect from memory performance. We can also in Mplus check our model structure to make sure that we estimated the correct model if we're not sure, by looking at the path diagram. So when you click on diagram and then view diagram, you can take a look at the generated path diagram for your model, and here you can see you get the unstandardized estimates shown right away in the model. This is a little bit cluttery. If you don't want to see it, you can go to view and then you can click on show no estimates to only view the model, and here you can see the model structure that Mplus estimated with the autoregressive paths, here the cross-legged paths, and then also the correlations between the correlation between the exogenous variables at time 1 as well as the residual association, which we saw was not substantial here. So this is a way to check, so to say, that Mplus estimated the correct model, and then also to see what Mplus estimated by default in case you're not sure. Then it can be helpful sometimes to take a look at that path diagram as well. I hope you liked this video to learn more about autoregressive cross-legged models. If you're more interested in longitudinal models, there are more videos on longitudinal SEM that you can check out here on this channel. Also, I teach courses on longitudinal structural equation modeling, including growth curve modeling and other models via QuantFish, and you can find links to those courses in the description here. If you like this video, then please subscribe to the channel, hit the like button, and I'll see you next time.